Good morning, students. Our second module is linear ordinary differential equations. In this topic mainly consists of homogeneous differential equation and non-homogeneous differential equation and its solutions. First, what is second order linear ODE? Second order linear ODE. What is ODE? Ordinary differential equation is represented by ODE. A second order linear ODE. ODE is an equation that involves an unknown function and its derivative. A second order ODE is said to be linear if it can be written as y double dash plus p of x y dash plus q of x y equal to r of x, where p, q, r are the functions of x, and if r of x equal to 0, it is known as homogeneous differential equation, and if r of x not equal to 0, it is known as non-homogeneous differential equation. And if r of x equal to 0, we can represent it as y double dash plus p of x y dash plus q of x y equal to 0. It is homogeneous differential equation. We have to find its solution, and we know that it has two solutions. Let's try an example. Let's second order linear differential equation. We can take y double dash plus y equal to 0. It is a second order differential equation. Let y equal to cos x and y equal to sin x are its solution. Then we can check it is correct or not. Y equal to cos x, so y dash equal to minus sin x. Then y double dash will be minus sin x. Derivative of sin x is cos x, so minus cos x. Then cos x is our y, so we can substitute here y. Then y double dash equal to minus y. When we are taking it into left hand side, then y double dash plus y equal to 0. So we proved that it is correct. Then next solution is y equal to sin x. Then y dash equal to cos x. Y double dash equal to derivative of cos x equal to minus sin x. So sin x is a y. Then substitute here y. Then y double dash plus y equal to 0. So this is also correct. So y equal to cos x and y equal to sin x are the solutions of this linear ODE. Next is solution of second order homogeneous linear ODEs. We know that y double dash plus p of x y dash plus q of x y equal to 0. Here p of x and q of x are the functions of x. Here r of x equal to 0, that means it is homogeneous linear ODE. Here p of x and q of x are, if p of x and q of x are constant, then we can represent it as y double dash plus a y dash plus by equal to 0. P of x and q of x are constant, which is represented by a and b. So our equation changes y double dash plus a y dash plus by equal to 0. Where y double dash is represented as d square y, that means second derivative of y. So y double dash we can represent it as d square, second derivative d square y, and y dash we can represent dy, first derivative of y. So replace it y double dash by d square y and y dash dy. So d square y plus a dy plus by equal to 0. So we can take y common, and d square plus a d plus b into y equal to 0. If lambda equal to d, we replace d with lambda. We can write it as lambda square plus a lambda plus b equal to 0. This is known as characteristic equation or auxiliary equation. The root of the characteristic equations are lambda 1 and lambda 2. It is second order equation, so we know that two roots exist, lambda 1 and lambda 2. According to the nature of these two roots, there are three type solutions for y. Here case 1, if lambda 1 and lambda 2, these two roots are real distinct root, then y equal to c1 e raised to lambda 1x plus c2 e raised to y2x. And if this lambda 1 and lambda 2 are equal and real roots, then we can write the solution y equal to c1 plus c2x into e raised to lambda x. And if these roots are complex roots like alpha plus or minus I beta form, complex conjugate roots, then y equal to, our solution equal to e raised to alpha x. Alpha means our real part, alpha x into c1 cos beta. Beta is imaginary part, cos beta x plus c2 sin beta x. These three conditions are exists for according to the value of lambda. Next we can do a problem. Find the general solution of linear ODE, ordinary differential equation, y double dash minus 0.25 y equal to 0. So directly we can write our auxiliary equation lambda square minus 0.25 equal to 0. That means our second derivative we represented by lambda d square is first. That means y double dash we can represent it as d square y minus 0.25 into y. So it is equal to 0. That means d square y, here substituting d square by lambda, so we can write lambda square minus 0.25 equal to 0. So our lambda is equal to plus or minus 0.5. It is distinct roots. So our first condition, the if the roots are distinct, that means lambda 1 equal to 1 by 2 and lambda 2 equal to minus 1 by 2. The roots are distinct. Our solution will be c1 into e raised to lambda 1 x plus c2 into e raised to lambda 2 x. Here lambda 1 is 1 by 2 and lambda 2 is minus 1 by 2. So our solution c1 e raised to 1 by 2 x plus c2 e raised to minus 1 by 2 x. This is our solution. Next we can practice some problems. The second problem is y double dash plus 4y dash plus 4y equal to 0. So we can directly write our auxiliary equation lambda square plus 4 lambda plus 4 equal to 0. Second derivative is represented by lambda square and first derivative is lambda. Here y is, we cannot write lambda here. It is, there is no derivation of y, so derivation of y is represented by lambda. Second derivative is represented by lambda square. So here we cannot write lambda here. So you have to notice that point. So lambda equal to minus 2 comma minus 2. These are our roots. So these roots are equal and double roots. So our solution will be, if roots are equal, our solution will be y equal to c1 plus c2x into e raised to lambda x. Here lambda is equal to minus 2, so here substituting minus 2 here. Third problem will be y double dash plus 2y dash plus 2y equal to 0. Auxiliary equation we can write directly lambda square plus 2 lambda plus 2 equal to 0. So here our solutions lambda equal to minus 1. We can calculate these roots by using our calculator. So lambda equal to minus 1 plus or minus I. It is a complex number. It has real and imaginary parts. Real parts alpha equal to minus 1, imaginary part beta equal to 1. So y, our solution y equal to e raised our, if roots are complex roots, then our solution will be y equal to e raised to alpha x c into c1 cos beta x plus c2 sin beta x. So e raised to alpha is our real part of our complex root. So alpha equal to minus 1, so equal to e raised to minus x into c1 cos beta is 1. So cos x plus c2 sin beta is 1 here. So sin x. This is our solution. Next is for fourth problem, y double dash plus 2k square y dash plus k raised to 4y equal to 0. So we can write our auxiliary equation, lambda square plus 2k square lambda plus k raised to 4 equal to 0. So our equation, we can write lambda plus k square whole square equal to 0. It is in the form of a plus b whole square. So we can write lambda plus k square whole square equal to 0. So lambda plus k square equal to 0. So lambda is equal to minus k square and minus k square. So roots are equal. So we can write, if roots are equal, our solution will be c1 plus e2x into e raised to lambda x. Here lambda is here minus k square. So we are substituting here. This is our solution.